We've previously looked at the set of Subat variables and the equations linking them, and how we can use this to describe motion with uniform acceleration in one dimension. Now we're going to spread out to 2 dimensions and have a look at projectile motion, which is actually just what we did last time, plus. So, let's make up for ourselves a nice question and work through an example. So let's say we're standing atop a cliff and we throw a ball off the top. Okay, so here's our cliff and we're going to launch the ball off of this. Let's say this cliff is 20 meters high, and this ball we're going to launch off at an angle of 15 degrees above horizontal, and we're going to launch it at 5 meters per second. And we want to know how far is this ball going to travel before it lands. So we know it's going to travel in a nice parabolic arc, and eventually it's going to hit the ground. So to do this, we're going to break up this velocity into its vertical and its horizontal components, as we've done with vectors before, and then we can treat the vertical components separately from the horizontal component using 2 sets of Subat variables, and we'll see what that leads us to. So the first thing we need to do is work out the vertical and the horizontal components. So our vertical component is the velocity, in this case is our angle over here, it will be 5 times the sine of 15 degrees, and the horizontal component is going to be 5 times the cos of 15 degrees. Punch that into a calculator. Then for our vertical component we get 1.29 meters per second. And for our horizontal component we get 4.3 meters. So, while the vertical and horizontal components are completely independent, there is one thing that is in common between them, and that is how long it takes for this path to complete. So when the ball lands, the ball lands, and that stops the vertical motion and it stops the horizontal motion. So everything else is independent except for the time, the duration of this. So let's write out our Subat variables. So we'll do one for the vertical, one for the horizontal. So we've got S, U, B, A, 2, S, U, B, A, 2. Now horizontally, we've got no acceleration. So actually, horizontally, we don't need a full set of Subat. We can simplify this a little bit. And once we've found our time of flight, so once we've found how long we're going to be in the air for, our displacement is just going to be our horizontal velocity times our time. So our horizontal velocity down here, and our time, which we're going to have to find down here. Now vertically, we know our acceleration is downwards, and so that's minus 9.81. Our final velocity, we don't know, and we don't need to know its final time. It doesn't appear so at the moment. Our initial velocity is upwards, so that's plus 1.29. And our displacement, we say we're going to finish 20 meters below where we started, so that's minus 20. So, if we want an equation that's got S, U, A, T, it would be S equals UT plus R, A, T. Now most of the time where we've come across this before, we've had 0 initial velocity, which takes this term to 0, and just leaves us with S equals a half AT squared, which is easy to solve for t, because 2 is 2S over A equals 2. However, in this case, this is non-zero. U is non-zero, so this term remains, and we get something that's quadratic in t. Why that's soluble with the solution for a quadratic formula, it's a bit of pain to do, and it's certainly very messy. So instead of doing that, let's find v after all. So if instead of finding t, we ignore t for now, find v, and then we can use an equation, a different equation to find t using this newfound value of v. Specifically, we'll be able to use v equals u plus a t, which would be a bit simple. But for now, we want the equation that's got a, b, u, and s. And that's v squared plus u squared plus 2x. Substituting to this, we have 1.29 squared plus 2 times minus 9.81 and times minus 8. So that's our a and that's our s. This will give us v squared, so then we'll want to root it. So once we work this out, take the square root of that, that'll give us our a. So when we punch this in, this gives us 394. So the square root of 394 gives us plus or minus 19. So because we've taken the square root, we're going to get plus or minus its value. And what that actually corresponds to, we can see at this point our velocity is going to be downwards, so our vertical component will be the negative 19.8. And what we've got in the positive 19.8 is the other solution is over here. So if we imagine extrapolating this back, imagine if rather than starting the launch here, this was part of the path which we continued backwards. We're saying its layer started here and upwards at 19.8. We don't need to worry about that. This is going to be going downwards at 19. So now we've got our v minus 19.8. We can substitute some values into here. So when we rearrange this, what we're going to get is t is equal to v minus u over a, which is equal to minus 19.8 minus 1.29 over minus 9.81. And that will give us a time 2.15 seconds. So we can see what we've done here is using our vertical components of this 2D projectile motion, we've been able to find the time that it takes for this object to complete its flight. We can now take this time and we can substitute it into our horizontal motion equation, and that will give us a total distance horizontally that we've travelled. So we take our time, we multiply it by our horizontal velocity, so 2.15 times by 4.83, and that will give us about 10.4. So this is the general method that we would use when approaching any projectile motion. All we've got is this suvat variable, so exactly the same as any other suvat problem. We've got one set of variables for vertical and one set of variables for horizontal. In general, we have no horizontal acceleration, so we'll actually just simplify horizontal to s equals v2. We first need to find the horizontal and vertical components of our initial velocity, which allows us to place values here, here, and then depending on what we're provided with and what we're after find, we can then find the remaining quantities by selecting appropriate equations and substituting values in the same way as we have done with all other suvat.